So now we're into, sorry, gotta wait for the key. Okay, now, yeah, we're into chapter 7, finished up chapter 6. We're talking about the control of microbial growth. And when we talk about control of microbial growth, again, I want you to remember what your focus is. Again, I'm trying to get you clinically oriented to microorganisms, the importance of what we talk about in its relationship with microorganisms typically relates to diseases that they cause. One of the reasons why we want to control microbial growth is if we can control microbial growth, hopefully it will prevent a number of diseases or contamination of wounds, which would lead to diseases, i.e. infections. And so it's important for you to understand mechanisms, metabolisms, for example. We talked about metabolisms last time. We talked about cellular structures. Some of the reasons why we talk about that is the antibiotics we use, the disinfectants that we use, temperatures that we use, cold extremes or hot extremes, will help control microorganisms. Either we can destroy the cell membrane or the cell covering of a particular microorganism. Perhaps we can alter the metabolism of a particular microorganism using a specific chemical or pharmacotherapy product. Either way, the reason why we talk about all those things is so we can help control microbial growth or in essence help treat a number of diseases. So some terms that you need to understand: sepsis is one of them. Sepsis refers to microbial contamination. Asepsis is the absence of significant contamination. Now, asepsis does not mean sterile. Sterile typically relates to the complete absence of any type of microorganism. Asepsis is the absence of significant contamination. So an aseptic field tends to mean that we've used some type of disinfectant. We've certainly significantly reduced the amount of microorganisms that would be on that surface, but it doesn't mean that it is sterile. Example of that: when you take a patient to surgery and you clean the area where the incision is going to be made, you scrub it with betadine solution, which is a very potent antiseptic, but it doesn't make the skin sterile. The skin will always have microorganisms. By scrubbing the skin, you have significantly decreased the amount of bacterial contamination. You have thus created an aseptic field, but you have not made that area sterile. Now, instruments, for example, metal instruments that we can put in an autoclave, which is basically a oven that heats instruments to an extreme temperature, will kill all microorganisms. When that procedure is completed, those instruments are sterile. There are no microorganisms on its surface. Different from aseptic or asepsis, okay? Absence of significant microbial or significant contamination. Aseptic surgery techniques prevent microbial contamination of wounds. Sterilization procedure, removal and destruction of all forms of microbial life. Then there are forms of commercial sterilization. This happens when subjects are canned food processing. The heat will help destroy the endospores. That was one of your lab responses. Endospores of Clostridium botulinum. Disinfection, destruction of vegetative pathogens on the surface, usually with chemicals. Spores and viruses are not necessarily destroyed. Antisepsis is the chemical disinfection of living tissues such as skin or mucous membrane. Again, chemical disinfection does not necessarily create a sterile surface, okay? Asepsis, absence of pathogens on an object or an area, again, as in aseptic surgery. Degerming or degermination is the removal of transient microbes from the skin by mechanical cleansing or by antiseptic. Sanitization, sanitation, whichever you prefer, is the reduction of microbial population on an object to safe public health levels. Now, this is different from asepsis. Again, this is acceptable reduction in microbial population, which means there is an acceptable level. Typically is low, it's not grossly contaminated, but a public restroom has tons of microorganisms. But you use sanitation procedures to maintain a reduction in the microbial population so it's safe for public health use. In general, the suffix CIDE indicates a killer. Now, the reason why I bring that up is because you'll see a lot of items sold over the counter. Bactericidal, bacteriostatic. Bacteriostatic substances will decrease the ability of these microorganisms to grow. Stasis stops them from growing. Cidal are typically mechanisms that help kill microorganisms, and thus if you kill a number of microorganisms, eventually you will attain a aseptic type of feel. A biocide or a germicide kills microorganisms. Fungicides kill fungus, fungi. Viricides kill viruses, and so forth and so on. Suffix stat, S-T-A-T. Suffix stat, used in a way to indicate that only substances are inhibited. Examples are bacteriostasis. Again, you have halted the growth, but it only indicates that you have inhibited the growth. It does not indicate that you have killed a significant number of microorganisms. So terminologies that you need to be familiar with: sterilization, commercial sterilization, disinfection, antiseptic, degerming, sanitization, biocide, germicide, and bacteriostasis. Now, bacterial populations killed by heat or chemicals tend to die at a constant rate. An example, 90% every 10 minutes are numbers that can be plotted logarithmically to figure out from a descending line, typically plotted on a graph, that you can illustrate the killing rate of particular types of substances that are used. Again, this is an example. Again, illustration taken out of your book, demonstrating bacterial population that die at a constant logarithmic rate depending on the type of substance, bactericidal, heat, extreme cold, whatever the procedure is using. You see a logarithmic drop or decrease in the population killed. Effectiveness of certain antimicrobials, again, depend on the number of microbes. The bacterial load you start off with typically will gauge the killing range. If you have a tremendous number of bacteria in a small area, you use a disinfectant, say, directly on top of them that has bactericidal properties. You can kill a significant number of bacteria in a very short period of time, which will significantly increase the steepness of that slope. However, if you have a significant amount of microorganisms spread over a large surface and only a small amount of substance that's bactericidal, it may take a longer period of time, and thus your slope will be more toward a horizontal type of a pattern. So it really depends. So effectiveness in antimicrobial treatment depends on the following: number of microbes, environment, whether it's organic matter, whether there's temperature involved, certain types of biofilms that may actually slow down the process of killing, the time of exposure, how long does the agent have in contact with the microorganism to be able to destroy it, and then the microbial characteristics. Obviously, some substances, some bacteria that you've already learned, have protective coatings. If they're an endospore and they're exposed to certain disinfectants, it may not even affect the microorganism. So it depends on the microbial characteristics. Also applies for if you're using heat and you have a microorganism that can live at extreme heats, then it may not affect the microorganism's growth pattern at all. So again, it will depend on the characteristics of those microorganisms. So activities and or actions of the microbial agents that are being used. Alterations in membrane permeability. Again, one of the reasons why early on we talk about the membrane, the cell membrane and or the cell wall, the covering around these microorganisms. Certain microbials may alter the permeability of membranes. If this happens, it may control or alter the ability of nutrients or waste to pass into and out of the cell. If you damage the plasma membrane, what is one of the things that this membrane does? It preserves the internal environment, which is typically different from the environment on the outside. So if we let the contents of the microorganism leak to the outside, it will cause harm to the microorganism. If we let the environment from the outside leak into the microorganism, then it can also cause damage as well. So alteration, changing the membrane permeability, can significantly lead to interference with the growth. Damage to plasma membrane causes leakage to the cellular contents and interferes with cell growth. Now, there are also proteins and nucleic acids. Again, from our previous lectures, we've talked about how you can denature proteins: extreme heat, altering the pH, extreme cold, changing the acid-base balance in a particular environment. So you can damage proteins, you can damage nucleic acids. Chemicals may denature proteins by reaching, for example, disulfide bonds, particular bonds that help bind these three-dimensional structures together. Chemicals and/or radiation may prevent proper replication and functioning of DNA and RNA. Again, at a nuclear level, the nucleic acids, those nitrogenous bases, have to bind in a specific sequence. If they don't bind in a specific sequence, they mutate. If you mutate a microorganism, then you can potentially kill it. Now, that doesn't always work to our advantage. Remember, there are a number of viruses, bacterial infections that are out there that mutate all the time. When they mutate, sometimes it's to mutate to become resistant to particular drugs and whatnot. So if that occurs, the mutation may not be beneficial. But typically, if we're trying to do this with a microbial control agent and we alter that DNA, the DNA sequence, then typically we will cause damage and destroy the microorganism. So alteration in membrane permeability, damage to protein, damage to nucleic acid are the actions of microbial agents. Now, heat, thermal death point, is the lowest temperature required to kill a liquid culture of a certain species of bacteria in 10 minutes. Thermal death point is the definition of that. Lowest temperature required to kill liquid culture of a certain species of bacteria in 10 minutes. Thermal death time is the length of time required to kill all bacteria in a liquid culture at a given temperature. And decimal reduction time, the D value, is the length of time in minutes required to kill 90% of a population of bacteria at a given temperature. Boiling at 100 degrees kills vegetative forms of bacterial pathogens, many viruses and fungi within 10 minutes. Endospores, you're familiar with again, endospores, and some viruses can survive boiling longer than this period of time. So what types of heat can we use? Well, we can use moist heat. Steam under pressure allows temperature above the boiling point to be reached. Autoclaves, retorts, pressure cookers, and vessels in which high steam pressures can be contained. Typical operation or operating condition for sterilization is about 15 pounds per square inch, 121 degrees at 15 minutes. Pretty much kills everything, but you know, there are still some microorganisms, believe it or not, that live in lava pits. So you can understand that there are some extreme temperatures out there for certain microorganisms. But for the ones that we're primarily concerned about in a hospital or clinical setting, typically in a typical operating condition for sterilization, 15 psi's at 121 degrees. You need to know that. Moisture must touch all surfaces in order to bring about circulation. Air must be completely exhausted from the container. The process may be limited by objects' stability under heat and pressure. So in other words, there are certain types of instruments, fragile instruments, ceramic plates, for example, that are used in surgical procedures that may not be able to tolerate these high temperature extremes. And so because of that, it may not be able to use these types of sterilization procedures. Again, this one specifically talks about moist heat. There will be dry heat that I'll talk about. There are chemical preparations that can be done for sterilization as well. This illustration is taken out of your textbook and basically demonstrates a pressure cooker. Moist heat, again, denatures proteins, kills microorganisms. Autoclave, basically steam cookers. Steam under pressure will destroy the majority of microorganisms that we are concerned about. You're already familiar with pasteurization. I'm sorry about the misspelling up there. Off one point. Pasteurization is mild heating that is sufficient to kill particular spoilage or disease organisms without seriously damaging the taste of the product. Now, again, pasteurization, not sterilization. Pasteurization. You know, you can keep the milk in the refrigerator long enough, and I don't care how cold it is, it's still going to taste bad after a couple of weeks. So pasteurization, mild heating, it kills sufficient to kill the spoilage types of bacteria or microorganisms. And again, it does it without seriously damaging the taste, because remember, milk has protein. You denature the protein that's actually in milk by heating it too much. You will alter the taste of different substances. So a lot of foods are dependent upon that. Anybody ever see the movie Cannery Row? No? With Deborah Winger? Anybody see that? You saw that? That's a great movie, isn't it? Cannery Row, and they had pasteurization process going on there. It was a factory went out of business. It's a great movie. Deborah Winger and Nick Nolte, before Nick got the drinking problem. But it was a good movie. Anyway, so watch it sometime. Dairies use a phosphatase test, which determines whether the product has been properly pasteurized. Now, phosphatase, where do you think phosphatase comes from? I'm sorry? Phosphatase is an enzyme. That's correct. Where does the phosphatase come from? It comes from the bacteria. The bacteria has phosphatase. So if we measure something and it has a high level of phosphatase, you got too much bacteria in the substance. So you do a phosphatase test to see if bacteria, a significant amount of bacteria is in a particular product. So the phosphatase test in this way is an indirect way of measuring the bacterial load in a particular substance. High temperature, short time pasteurization uses temperatures of at least 72 degrees for about 15 seconds to pasteurize milk. This is a big procedure that's done now, and the milk just kind of rolls down a tube, and the tube is heated, and again the milk would be exposed to that temperature for that period of time, and milk can, you don't have to slow down the production of milk into containers. Equivalent treatments are illustrated by some other examples. Heating 115 degrees, acting on an organism for 70 minutes is equivalent to heat at 125 degrees, acting on an organism in 7 minutes. There are little formulas that you can put together to be able to get these numbers. Milk can be sterilized and stored under refrigeration when given ultra-high treatment, which is another mechanism that can be utilized as well. Again, as a review, pasteurization, you're familiar with, reduces spoilage of organisms and pathogens. Equivalent treatment, 63 degrees for 30 minutes. High temperature, short time, 72 degrees for 15 seconds, so forth and so on. I'm sorry? Yeah, going fast. You've already read this chapter, though, because you remember the test was going to go to chapter 9, so that's why I figured I could just move right through this. Okay, thermal death point, TDP. Lowest temperature at which all cells in a culture are killed in 10 minutes. And I'm glad you brought up that point. I'll digress for a minute. On Tuesdays, that's your time to really, that's actually prescribed study time. So you'll have an opportunity to go back through these lectures, because I'm recording them now, so it'll be posted for you. So you'll be able to review the lecture again. So if information is a little too fast for you, if you hadn't had a chance to read before the time of the lecture, you'll be able to play it back over and listen to it again. So from this point on, all the lectures will be recorded and posted for you on that site where the review was at. Okay? Everybody got that? All right. So the other thing, thermal death time, TDT, time to kill all cells in a culture, and decimal reduction time, DRT, minute to kill 90% of a population at a given temperature. So thermal death point, thermal death time, and decimal reduction time. Incineration, many of us are familiar with incineration. This is direct flaming. It's efficient, but it has limited purposes. Again, certain substances we can't incinerate because it's kind of like throwing the bathwater out with the baby. So incineration, again, great dry sterilization procedure, but it has significant limitations. Hot air sterilization, as in the oven that we talked about before, you have significant temperature elevation, but we don't have moisture going on here. But this will ensure sterilization. Then moist heat is generally more efficient because you've actually increased the surface areas. The water molecules are heated. They hit more of a surface. There are more water molecules available to contact surfaces, so typically it's more efficient, but again, limitations would be whatever the substance is that you're trying to sterilize. Okay, dry heat sterilization kills by oxidation, flaming, incineration, hot air sterilization. Equivalent temperatures 170 degrees in 2 hours. An autoclave 121 degrees for 15 minutes under pressure. There are also filtration methods you can use to achieve a decrease in microbial growth. and number. Liquid sensitivity to heat can be passed through a thin film membrane, basically a filter, and is carefully controlled. The pore size, which will retain microorganisms. Certain microorganisms are of certain sizes, typically measured in nanometers, and I'm not going to ask you to know the size of microorganisms, but the filtration method works by passing a liquid substance, liquid sensitive to heat, can be passed through a thin film or a thin membrane, and literally the microorganisms are filtered out. Operating theaters, special clean rooms receive this by passing through a high efficient particulate matter or particulate air filter, a HEPA. Those of you who will work in oncology, when you prepare certain chemodynamic agents, you're in an operating theater that uses a special clean room because it receives air that's passed through these types of filters. There actually are hoods that are set up that will work under the same type of mechanism, where air will be passed, particulate matter will be removed based upon the type of filtration system that's used. Refrigeration, refrigerated temperature, 0 degrees to 7 degrees, slows the metabolic rate of microbes. However, psychotrophic species will still grow slowly. So some of the organisms, again, that will grow in milk are psychotrophic organisms. You can certainly slow the growth, and so you can keep the milk in the refrigerator for up to 2 weeks, but after 2 weeks, I'm using a relative number here now that may not be correct for the brand of milk that you buy, but typically about 2 weeks, then microorganisms will begin to be at a certain bacterial load. There will be a growth phase that will occur in the bacteria that are psychotrophic, and eventually you'll have a high bacterial load there. Some organisms grow at temperatures slightly below freezing, but microbes at the usual temperature of a freezer compartment are typically completely dormant. High pressure, and as we talked about, high pressure used with heat. Now just high pressure alone. High pressure applied to liquid suspensions such as fruit juices can kill vegetative bacterial cells. Endospores are relatively resistant. An advantage is that flavors, colors, nutrient values are preserved if you simply use high pressure. Think about the compressive forces that are typically necessary to be able to compress a microorganism, significantly changing the pressure. We're used to atmospheric pressure of about 760 millimeters of mercury. Increase that pressure significantly, it will affect the microorganism. So there is a compressive nature that allows you to be able to do that. Desiccation, microbes underwater for growth. Adequately dried or desiccated foods will not support growth. Osmotic pressure can be used. Again, high salt, high sugar concentrations. Back in the days of yore, all they had were salt. So meats were processed by dipping them in heavy amounts of salt, which would significantly change the osmotic pressure of meat. And so bacteria wouldn't grow on those particular types of in the environment of this particular type of preservative, because it would alter the osmotic concentration. Water inside the microorganism would be pulled out or drawn out by osmotic pressure, and these organisms would die. So salt is still used in that same form. You may be familiar with beef jerky, though they make it a little bit differently these days. But back in the day, that was the only way they had to preserve certain types of meat. Generally, mold, yeast resist osmotic pressure, so it's better for bacteria. So you kind of have to brush off the mold, but you can eat mold and yeast, so brush that off and go ahead and eat the meat. Filtration removes, I didn't say you had to, I'm just saying it's an option for you there. Physical methods for microbial control, again, filtration, just as a review, refrigerating, deep freezing, lyophilization. Was that on the test? Okay, very good. Okay, high pressure, I don't even need to go into it. High pressure denatures protein, desiccation prevents metabolism, osmotic pressure causes plasmolysis. In other words, draws the fluid out, cell will collapse, and or it can work vice versa, where it's hemolysis, or where basically water osmolysis, where water will come into the cell and will rupture that way as well. Ionization, radiation, such as X-rays, gamma rays, high energy electron beams that carry high energy and break DNA strands. Ionization radiation forms reactive hydroxyl radicals. These are very unstable particles, typically are very destructive. Such radiation is used to sterilize pharmaceutical products. Non-ionizing radiation such as ultraviolet or UV light has a long wavelength and has less energy. UV light causes bonds to form between adjacent thiamines in the DNA chains. Thiamines, again, are those nitrogenous bases, one of the nitrogenous bases. Penetration is low. Sunlight, some biocidal activity may be due to the formation of a singlet octet, which again is kind of a free radical in the cytoplasm. So there are different forms, again, illustrated through radiation that can be used. Ionizing radiation and non-ionizing radiation. Again, ionizing radiation we commonly are familiar with: X-rays, gamma rays, electron beams. Non-ionizing radiation, microwaves killed by heat, not especially antimicrobial. This is just a spectrum of light. I'm not going to hold you to remember that. Evaluating disinfectants. Chemical methods for microbial growth. The relative effectiveness of disinfectants is determined by the tests such as phenol coefficient test. Bacteria are tested under a standard condition against concentrations of phenol and a test disinfectant. Phenol being the standard, and comparing that with any other type of disinfectant. Now on TV you see the products kind of compete with themselves. Some disinfectant products like Lysol, I don't know about Mr. Clean and Ammonia Johnny and all those, but Lysol typically has phenol, and so you'll see a lot of other products will compare themselves to that as the standard. But typically in a pure lab, they use a generic form of phenol and compare other agents to it, single agents, to determine whether or not the antimicrobial control rate is effective by that agent. In the American Official Analytic Chemistry, they use a dilution test, a series of tubes containing increasing concentrations of a test disinfectant. They are inoculated, or a bacterial load is introduced, is incubated or cooked for a period of time. When I say cooked, I mean it's put in a perfect temperature room that bacteria would typically grow. So you inoculate these test tubes, inoculate it with bacteria, you introduce a bacterial load, then you put it in an incubator where the temperature conditions are ideal for this microorganism to grow. The more the chemical can be diluted and still be effective, the higher its rating. Now, the cure to pollution is dilution. Cure to pollution is dilution. Dilution is the key. Any substance, any chemotherapeutic agent, aspirin, Tylenol, Prilosec, Nexium, penicillin, any chemical substance, Lysol, that you use at a high enough concentration can kill. Okay? Now, at the right dilution, those organisms, that chemical may be therapeutic. I can give you a massive dose of aspirin and kill you with it, but I can give you a therapeutic dose and alleviate pain or fever. Okay, so any chemical substance, again, dilution is the key. We can dilute substances. So again, what we want to do in this particular type of test, you have a agent, phenol for example. We dilute it over and over again serially. Again, the more the chemical that can be diluted, if you can very much dilute it and it still be effective as an agent, then that agent gets a much higher rating. Okay, so this is American Official Analytic Chemistry used for dilution. Okay.
When you speak of dilution, is that adding more of the phenol itself?
No, that's adding more of a solvent that would dilute it, that would lower the concentration of phenol. Lower the concentration of phenol. As you continue to dilute it, lower the concentration of phenol, and it still controls microbial growth, then that's the agent. That's your benchmark. You want to compare any agent that you're going to use as a disinfectant or a bactericidal to phenol. And so you want to dilute it, dilute it, dilute it, dilute it. The least amount of that chemical you can use and still cause a killing zone, more or less, for bacteria. That's the agent that you want to use. Now, one of the things that we do in labs, say we, I'm not a microbiologist, so I say they do in labs, but you need to know who they are. A disc or a filter paper is sometimes soaked with a chemical agent, and it's placed on an inoculated surface, like an agar plate. So take the agar plate, Let's take a selective median, and we have a particular microorganism that's growing on it. And then we take a disc or a little piece of filter paper. It's been soaked with a chemical agent, a chemotherapy agent, antimicrobial, whatever we're going to use. We drop that on the agar plate where the bacteria is growing. What we hope to see, if we want this agent to work, is we want to see a clear zone form around that disc or that little piece of filter paper that we dropped on the solution. And this is what's used all the time in microbiology labs or in a laboratory that's used in a hospital. You're trying to determine whether or not the antibiotic that you're using is going to kill this particular bacteria. And you take a disc, a penicillin disc, and you drop it on the plate where the bacteria is growing. And in a day or 2 days, you'll see a clear zone around the disc, which indicates inhibition of growth. So, chemical methods again, principles of effective disinfection, concentration of the disinfection, organic molecule, organic matter, carbon-based, pH, acid-base balance, and or the time. Sometimes an agent may work if you give it a long enough time. Depends on if you have that period of time. Penicillin will kill staph as long as the bacterial load is not so heavy, or the concentration or the dose you can give of that particular agent would be able to kill the number of organic matter that you have there to be able to be destroyed. So all of those are factors involved in these chemical methods. Evaluating a disinfectant, again using a dilution test that I already talked about. These are some discs that utilized the clear zone method. Again, you can see where these little individual discs are dropped on the culture median. You see examples of Staphylococcus aureus, Escherichia coli, Pseudomonas aeruginosus. These are all microorganisms that are growing on particular plates. Particular tabs, chemical tabs, have been dropped. As you can see, chlorine, phenol has been used, chlorophene has been used, quat has been used, which is a control. All of these have been dropped on, and you can see zones of clearing on the first plate. Some of the microorganisms, for example, look at Pseudomonas. You see hexachlorophene doesn't work at all on it. You look at the zone of clearing around chlorine on all of them. It seems significantly effective with the Staph aureus, somewhat effective with Pseudomonas aeruginosus. So if you had a choice of using an agent, chlorine would be the one you'd want to choose if you wanted to get rid of Staph aureus. Chlorine again wins out in E. coli, and to a similar degree chlorine, but you would probably want to use even a second agent with Pseudomonas aeruginosus because the zone of clearing that we see around the chlorine is not as marked as what we see in some of the others. And the others, if the bacteria is growing over it, if you got to pick it out of the bacteria, then it typically means it's not controlling the growth. So phenol, carbolic acid, seldom used today, very caustic to tissue, used to be used a long time ago, but phenol, a derivative of the phenol molecule, used to be widely used. Phenolics injure plasma membrane, inactivate enzymes, and denature proteins. So for necrotic tissue that's already dead, phenol is good. If you need to kill a bacterial load in a wound, the wound is nasty more or less, it's necrotic, dead tissue, bacteria load is there that you can see colonies, that's not a good thing, then dump some phenol in there. It'll clean it out. Now the bad thing about phenol though is the good tissue, the normal tissue, will get injured because the chemical contact of phenol on plasma membrane not only will destroy that tissue, but will inactivate enzymes and denature protein. So it has limited use, and again, it's not used very much at all today. There are other products that are out there that are more tissue friendly. They are stable, persistent, not sensitive to organic matter. O-phenylphenol are basically called cresol, basically the main ingredients used, as I said, in Lysol today. Phenol derivatives, bisphenol, contain two phenyl groups connected by a bridge. You don't have to worry about that. Hexachlorophene, basically the main ingredient in Physohex. Should be familiar with that. Physohex. Physohex, you'll see that used a lot in surgical settings as well. Betadine is probably the soup du jour in most hospitals to use as a disinfectant, but for people who are allergic to betadine or iodine products, typically you can use a substance such as Physohex, which again has hexchlorophene in it. and this will control at least gram-positive organisms primarily on the skin. Remember, when you're trying to establish an aseptic field on the skin, you need an agent that's going to reduce gram-positive organisms such as staph or strep. Again, does not sterilize. It will create an aseptic field, but it does not sterilize. Excessive use can be used in neurological damage, so don't want to use it too much in the wrong type of person. Triclosan, this is a widely used bisphenol found mainly in household products. Broad spectrum activity. Broad spectrum activity means it kills a number of different types of microorganisms. Can kill all the gram-positive bacteria, so it has broad spectrum activity. It may even kill some gram-negative bacteria as well, a broad spectrum. The term broad spectrum is used, person comes into the hospital. You know they have a pneumonia. They have a high temperature. You hear rattling in their chest. They got a productive cough. They're able to give you a sputum specimen, cough up some sputum in a cup. You take it down to the lab. You do a gram stain right away. It's a gram-positive organism, circular, cocci, in clusters. You got probably a Staph aureus pneumonia. You can use a broad-spectrum antibiotic to kill it. Now, over the next 2 to 4 days, you'll do a culture. You'll specifically take out that particular organism, grow it on a medium, then you'll look at it under a microscope and be able to specifically identify the bacteria. But in the interim, you can start the patient on a broad-spectrum antibiotic to treat that infection. And so that's why gram-positive, gram stain is so important. Gram-negative organisms, you brought the person in the hospital, coughed up, got a sputum specimen, took it down to the lab, and you have a gram-negative organism, and you found out that the person was in the hospital for the last 4 days and was discharged yesterday. He has a gram-negative bacteria found on his sputum. That's a much more significant infection. Not that the gram-positive guys aren't bad, but the gram-negative guys can kill you, and they can kill you fast. That person goes on 2 antibiotics at high doses right away. Okay, so the gram stain is real important. Can you still use a broad-spectrum antibiotic? Yeah, but you'd pick a broad-spectrum antibiotic that's more specific for gram-negative organisms. So this allows you to gauge your treatment right away based upon the activity of the gram stain. That's a little digression back into what we talked about before, but it's clinically applicable, and so it's important that you understand gram-positive, gram-negative. Okay, there's also these substances, bisphenol, triclosan, also effective against gram-negative bacteria and some fungi. Chlorhexidine, you may have heard of before. It's used pretty popularly, and it's over-the-counter now. Member of a biguanide group. Basically, it's not a phenol. Structure and applications resemble hexchlorophene. It's frequently used for surgical preparations, surgical scrubs. Again, they have little surgical scrubs when you are doing surgical procedures. You scrub your hands with for a certain period of time, wash underwater. I never really understood that because the water that you use is not sterile and you wash your hands, but that's how it works. So, but anyway, so if you work in a surgical setting, you'll see that. These are the chemical structures. I'm not going to ask you to draw out chemical structures at all. Iodine, another agent that many of you may be familiar with. Grandmothers loved iodine. Mothers love iodine. Basically, iodine is effective against all kinds of bacteria, also many endospores. You see that recurrent theme of endospores. Endospores are important because they help these bacteria be resistant to different types of disinfectants. But also, iodine will work against endospores, fungi, and some viruses. Mechanism of activity may be a combination of amino acid tyrosine. This is an enzyme, and cellular proteins. So mechanism activity may be known to be in combination with amino acid tyrosine. This is an enzyme. Enzyme products and cellular proteins are important. Again, if you have an activity, an enzyme that you can affect the enzyme, which is basically another form of a protein, then you can denature that with these types of substances. It would work. And then another substance is iodine-based. It's tincture of iodine, which basically means it's an aqueous alcohol solution that you would be able to use. It works the same way. It's going to attack a particular protein in that microorganism, maybe the protein for enzymes for cellular activity. that will denature it and prevent growth of the microorganism. Yes?
Why are some people allergic to iodine? Like, what
Uh,
is the body feeling?
Yeah, this is various individuals have sensitivities. You have developed antibodies over time, either to different types of chemical agents or to different types of reactants in the environment. Why a particular individual develops these allergies to others may be a genetic predisposition. It may be that you were exposed to a substance before and you developed antibodies to it, and now those antibodies are in your system, and when you get exposed to that agent again, the antibiotic attack made by your immune system, now so these are not antibodies that you take into your system but made by your immune system, will significantly attack those organisms, and you become sensitive to or allergic to certain agents. Why some individuals over another, again, could be genetic predisposition. It could be because you were exposed to something before and that's what has caused it. So it depends, and it may vary from individual to individual. So the other substance that you'll see used clinically would be iodophores. You see iodophore used a lot in gauze type preparations. Different types of sterilized gauze have been soaked in iodophore solutions. This is a combination of iodine and another organic molecule. Iodophores don't stain, but they are somewhat less irritating than iodine, but they can be irritating. Examples of these are iodine and betadine. These are forms of iodophores. Chlorine is used as a gas or in combination with other chemicals. Chlorine gas is basically used for disinfecting municipal water supplies, swimming pools, and sewage. And it can be very toxic. Chlorine gas spills, you may have heard reported. Last major one was in South Carolina, I believe Graniteville, South Carolina, where several people were killed from chlorine gas spills. So again, dilution, solution to pollution. Again, when you see chlorine exposure, you can dilute chlorine down to an effective amount where it can be used as a great disinfecting agent, and even to a point where we can ingest chlorine. However, at the wrong concentration, if it's not diluted appropriately, it can be very irritating. It actually, when chlorine gas comes in contact with the mucous membranes on the body, it turns into a form of hydrochloric acid and causes significant irritation. So that's why you get a lot of that's why you get a lot of coughing, choking from exposure to chlorine gas. So very important to note, if you're going to use chlorine, it's got to be diluted appropriately. Obviously, in municipal water, where that's the water supply for the public, certain levels have to be maintained. Sodium hypochlorite, ordinarily a household bleach, also a good disinfection. Same thing. Remember, dilution, key to pollution. If you dilute sodium hypochlorite, you can ingest it. It's actually a great disinfecting agent. There are actually chlorine pills. There's actually sodium hypochlorite pills, tabs that you can use, drop in water, and disinfect it, even in areas or even in water that has a heavy bacterial load. But again, it's got to be diluted properly at the right dilution. It's not a pollutant anymore. It's something that actually can control bacterial growth. Again, control bacterial growth, does not sterilize. That's the key. It does not sterilize. May make your swimming pool really clear, but it's not sterile. Chloramines consist of chlorine and ammonia. They're more stable than most of the chlorines that we see used. The U.S. military uses different types of agents. Here's another agent that's used by the U.S. military, sodium chloroisocyronate, which is basically a fill or disinfection for water. Biocidal actions of all chlorine based upon the formation of hypochlorous acid, which we'll see in water. Then one other factor in the effectiveness is the neutral charge, which allows it diffuses rapidly into water into the cell. Then chlorine dioxide is a gaseous form that's used in areas of disinfection, most notably to kill the endospore of anthrax. At the end of the semester, we'll have time to go through some of the bioterrorism agents that are used out there. I actually teach a bioterrorism course, and we talk about the different ways you're able to treat these types of attacks. But again, chlorine dioxide, gaseous form, used in area disinfection, again used to kill the endospore of anthrax. Anthrax is a great bioterrorism agent because it has an endospore, so it's resistant to a lot of forms of treatment that we used. And then just quickly as an overview again, halogens, iodine, chlorine, oxidizing agents, bleach, hypochlorous acid, some of the agents that we see used. Alcohols also could be used, both ethanol and isopropanol, which is rubbing alcohol, widely used, normally at a concentration of about 70%. Concentrations of 60 to 95% are effective. They are bactericidal, fungicidal, and are not effective against endospores or non-enveloped or non-enveloped bacteria. Alcohols enhance the effectiveness of other chemical agents. Just an overview again, this table is taken out of your book. Alcohols, ethanol, isopropanol, denature proteins. Again, if you denature proteins, you take them out of their quaternary, tertiary structures, then they are no longer effective. You'll see also alcohols can be used to denature lipids. Lipids are located where? In the plasma membrane around microorganisms. Denature or dissolve the lipids. You've destroyed the cell membrane. You've opened up the environment on the inside of that microorganism to the outside environment. You kill that organism. Now, heavy metals and their compounds as well. Tiny amounts of heavy metals are effective as antimicrobials. They can be illustrated by oligodynamic actions. Silver coin on an inoculated nutrient medium will inhibit the growth for some distance. Thus, we see used in preparations. 1% silver nitrate solution has been used to prevent gonorrheal infections in the eyes of newborn. Mom has an active gonorrheal infection. Baby comes through the birth canal, gets exposed to gonorrhea, can lead to significant neurological problems and or ocular problems related to the infant. So at the time of birth, this used to be across the board. Every baby that was delivered got silver nitrate put in the eyes. Not that it was a bad thing, but it prevented gonorrheal eye infections in newborns. So silver sulfasalidine basically was used. Also, we see that used as well for wound dressings for burn patients. Still a very popular application used in patients with burns because the silver sulfadiazine, it basically causes or creates another covering. When you had a burn, basically you lose areas of the integumentary system, so you lose a tremendous amount of moisture through the skin. You lose the ability to maintain body temperature. You also open yourself up, the body up, to a number of attacks from microorganisms that live on the skin or in the environment. So using the silver preparation in a wound dressing, you basically paste this on like a thick, heavy salve. It's a white cream, and basically it will help preserve some body heat. It also is a great antimicrobial. Silver combines with sulfhydryl groups on proteins and actually will denature the protein, so thus affects the protein being in the plasma membrane, proteins responsible for DNA replication. So again, if you can denature the proteins in these microorganisms, you will certainly be able to kill them. Mercuric chloride is a highly bactericidal but toxic, corrosive, inactivated by organic matter. Organic mercury compounds such as mercurochrome, you may have heard of that before. My grandmother loves that mercurochrome. That stuff is just burns, man, if you put that on a wound. But it can be used somewhat less irritating and toxic than inorganic mercuries, but can't tell me that from my childhood experiences. Copper sulfate, often used to destroy green algae in reservoirs and other waters. Zinc chloride is used in mouthwashes. Zinc oxide is used in paints as antifungals. Heavy metals, silver, mercury, copper, all used. Oligodynamic action, denature proteins. There are surface active agents that can be used as well. We may be more familiar with those as soaps and detergents. Examples, though they're less effective than many of the other agents that we talked about earlier. Will emulsify oils. They're good for denaturing agents. Acid anionic sanitizers are important in cleaning dairy equipment. Quaternary ammonia compounds, or quats, they are most effective against gram-positive bacteria but less effective against gram-negative bacteria. Again, you saw using the quat in the culture medium early on helps to determine when you see the zone of clearing, again, that we know that they're most effective against gram-positives. If we don't see inhibition of growth, sometimes we can make the correlation that this must be a gram-negative organism. Cationic detergents have good fungicidal, amoebocidal. Amoebas we hadn't talked about, they're one-celled organisms as well. Virucidals, viruses, are enveloped virus activity, but they are not sporocidal. So anything that produces spores may not be inhibited by the use of quaternary ammonias. Typically, they're colorless, odorless, tasteless, non-toxic, stable, inactivated by organic matter. Again, some examples are of Pseudomonas bacteria. Pseudomonas aeruginosus was the one I showed you earlier. Act by disrupting the plasma membrane and denaturing enzymes or denaturing proteins. So recurrent theme, as you can see with most of these substances, denature the plasma membrane or denature the enzyme. An enzyme is a protein, denaturing the protein. Widely used examples are quartz or benzalkonium. You also can see zephyrin. You may have heard of that before. It's used in a preparation. Cepacol, you may have heard of before. Cetylpyridium and chloride. Cepacol. You guys heard of Cepacol before, right? Cepacol mouthwash. Surface agents, surfactants, basically soaps and or degerming agents. Again, just as a review. Chemical food preservatives that can be used. Now, these are preservatives, so they inhibit the growth of microorganisms. Again, they may not kill microorganisms, but they'll inhibit the growth. So typically, these foods have to go through some type of process to decrease the microbial load. Pasteurization would be a good example. Some type of heat or canning procedure, and then an additive, a preservative, is put in the food. Sorbic acid, potassium sorbate, inhibits mold spoilage in foods such as cheeses. Benzoic acid, these are all the additives that you see added onto the food label. Antifungal, used in soft drinks and other acidic foods. Methyl paraben or propylparaben, these are substances that are also used, derivatives of benzoic acid. They work on neutral pH. They also inhibit mold, liquids, cosmetics, shampoos. Calcium propionate, which prevents mold growth in bread. All of these are organic acids that inhibit enzymatic and metabolic activity. Their activity is not related to acidity. And sodium nitrate, sodium nitrite, added to meat products. They can produce a red color, inhibits the outgrowth of botulism endospores, Clostridium botulitum. You already studied in your lab. Active principle is nitrite ion. Bacteria in meat reduce nitrate to nitrite. Nitrosamines, formed by reaction between certain amino acids and nitrites, possibly carcinogenic. Again, depending on the dose rate, cancer-causing agents. Now, can you use animal studies to determine whether or not substances are cancer-causing? Animal studies, mice. Yeah. Can you use it in court? In court, litigation, animal studies. Animal studies you can't use in court. They only determine a safety range. That you cannot directly correlate the data that you find from animals to humans. This is why metabolism in animals are completely different. The enzymes that they use to break down certain products, completely different. The metabolism inside their liver and our liver, completely different than what we see in humans. So we get safety ranges. Organizations like the Food and Drug Administration try to determine safety. Public health officials, OSHA, they use animal studies to help to determine safety ranges, but they are not. This is not data that you can apply to human health conditions. It is not acceptable in court at all to be able to use animal studies. There's a difference in how the levels of nitrosamine affect a mouse versus how it would affect a rat, because the metabolism in mice are different from the metabolism in rats, much less the difference between nitrosamine levels in mice compared to nitrosamine levels in what they may cause in humans. So all they're good for, I shouldn't say all they're good for, but primarily what you use these levels for, like nitrosamine levels, you try to correlate that with their cancer-causing ability in mice. That's only to determine a safety range. Food and Drug Administration wants to be extremely safe, and so if they use 200 times the dose in a rat and it causes cancer in the rat, then they'll at least have a safety range that they can apply for humans, because they know we can tolerate higher dosages in a human population. But for the purposes of litigation, it will not hold up in court. You can't say I exposed a rat to a particular agent, saccharin for example, and I gave this rat 200 micrograms of saccharin over 3 months and it developed liver cancer, so I drank Coca-Cola which had saccharin in it and I got cancer. The food company should have known that I would get cancer from drinking saccharin. That would get thrown out of court because you cannot use the study that was used in rats. You have to use human studies to be able to determine that. Certain substances that are toxic in humans may not be toxic in rats. Same thing applies to the rats, to the mice, to the humans. So that's just one example, but I want you to know that because there's a lot of fallacies out there about, oh, well, this substance must cause cancer because it caused cancer in chimpanzees. Chimpanzees I shouldn't use because they are pretty close to us, you know. But anyway, you cannot use animal studies. So just so you know that. Antibiotics. This is the meat of today. Is just the antibiotics. Knowing that few antibiotics not medically useful. They're used as food preservatives. They include niacin, which is bactericidin, protein produced in bacterium that inhibits another, which added to cheese inhibits endospore formers. Another one, and these were all tried to be antimicrobials in humans, but another one is natamycin. This is basically an antifungal that's used in cheeses. Once thought to be used as antibiotics, but now we know that they cannot be used. And this is just a summary. Again, chemical food preservatives, organic acids, what you want them to do, inhibit metabolism, sorbic acid, benzoic acid, calcium propionate. They control mold, bacteria in foods and cosmetics. Nitrites prevent endospore germination. Antibiotics such as niacin and natamycin prevent spoilage in cheese. Formaldehydes, that's a biggie that's used. Most effective antimicrobial are the aldehydes and formaldehydes. In the form of aqueous solutions, this gas is called formalin, very much used in preservatives of biological specimens. Glutaraldehyde, which is less irritating in 2% solution, also known as Sidex. Those of you who may work in a clinical setting may be familiar with Sidex. It's a bactericidal solution, tuberculocidal, virucidal in 10 minutes. It is a sporocidal after about 3 to 10 hours of contact with a particular substance. Both glutaraldehyde and formaldehyde are used in embalming. A possible replacement for glutaraldehyde is orthoaldehyde or OPA, which is seen used more commonly now. Aldehydes basically inactivate proteins, either proteins, enzymes, or cell membrane, like I said, a recurrent theme. Inactivate proteins by cross-linking the functional groups. Those are the functional groups. You've already looked at those before. Carboxyl groups, hydroxyl groups, so forth and so on, glutaraldehyde and formaldehyde. Then there are gaseous chemosterilizers, ethyl oxide. That is, they combine organic functional groups of proteins. It is a sterilant that kills all microbes and endospores and great for penetrating power. It's used to sterilize disposable medical equipment and equipment used in hospitals when heat treatment is not practical. Remember, disposable equipment typically is going to be made out of a plastic, though they have some disposable equipment they make out of aluminum-based substances, but they may not be able to take the pressure and or the heat that you can use when trying to treat them using an autoclave. So this is another option that you have. Propylene oxide and beta-propyroxidone basically are important gaseous sterilants. These gases are suspected of being cancer-causing agents as well. Plasma gas sterilization procedures make use of hydrogen peroxide vapor. Hydrogen peroxide is kind of a free radical. It's unstable as well, destroys cell membrane. Subjected to microwave and radiation, it can produce a very reactive free radical. And then gases, oh, I'm sorry, go ahead. 10 till. You can leave now if you want. Don't let me keep you. No, I'm just joke. That's a joke. It's fine. Gaseous sterilant, denatured protein, ethylene oxide. Peroxygens exert antimicrobial activity by oxidizing cellular components. Hydrogen peroxide is a common household antiseptic that's used. It's not a good antiseptic for open wounds, but it will keep deep anaerobic wounds where oxygen is released in the action of enzyme catalase in the tissue, so it's effective against anaerobes, especially Clostridium. Now, peroxygenes, or oxidizing agents, can be a little tough on the tissue as well. We may all be familiar with the use of hydrogen peroxide, pouring that in the wound and seeing the bubbles kind of create from that. It basically is a radical as well, so it's very good in using deep, nasty wounds, especially wounds that have necrotic tissue in it. But it can, over time, be a little tough on the skin, but again, works real good with Clostridium. Benzoyl peroxide, ozone, peracetic acid, all of these are effective types of chemical agents. As you can see, benzoyl peroxide, which we use in acne treatments a lot now. Deep wounds, also used as the main ingredient, again, as acne medications. Ozone, O3, highly related to oxygen generated by high voltage electric charges, and often the supplemental chlorination of water treatment, and peracetic acid, again, liquid chemicalization procedures. Then chemical antimicrobials that are not uniformly effective against microorganisms. Gram-positive bacteria, relatively more resistant than gram-negative. Viruses with an envelope, lipophilic types of organisms are susceptible than those of only a particular protein coat. And then endospores you already know about. They create a significant amount of resistance for certain microorganisms with the use of chemical agent. Mycobacterium, such as tuberculosis, has a waxy cell wall that makes it relatively resistant as well. And then prions, which are basically infectious proteins, are called, and they cause neurological diseases. Mad cow disease is the primary disease that we see in the public or on the media these days that prions cause, basically infectious proteins. Normal autoclaving at high temperatures, 134 degrees, solution of sodium hydroxide is recommended for this. Incineration may be used in some cases, and typically the carcasses of animals that are infected by these substances. This is basically a chart out of your book. At the top of the chart is the most resistant organism. At the lower portion of the chart is the least resistant organism. I would be familiar with that chart. I would be familiar with the order, not that I would ask you to write out 1, 2, 3, but you certainly should know prions, endospores, mycobacterium are much more resistant than what we see in gram-positive and our virus envelopes, because viruses are very fragile. Gram-positive organisms are as well. And this is just a chart in your book, too, that you can review at your leisure that basically just shows the effectiveness of certain agents against endospores.